Hey everyone, and welcome. Today, we're diving deep into the invisible world of sound. We're going to figure out how a simple little vibration can end up letting us see in the pitch-black depths of the ocean. It's pretty amazing stuff.
But first, let's kick things off with a classic riddle, one that sounds a bit like a magic trick. Is it actually possible for something to create a real physical vibration but make absolutely zero sound? And no, I'm not talking about hitting the mute button. This is a real physics puzzle, and trust me, by the end of this, you'll know the secret. So here's our game plan. We'll start with the basics. What even is a sound wave? Then we'll get into how to describe them. After that, we'll see what happens when sound bounces around, uncover some of its hidden superpowers, and finally, see how it all comes together in incredible tech-like sonar. Alright, so before we jump into the really cool high-tech stuff, we've got to get the fundamentals down. Let's break down the most basic question of all. How does sound actually get from, say, a guitar string to your ears?
Well, at its very heart, sound is just a form of energy that's born from a vibration. But, and this is the most important part, that energy can't just travel on its own. It absolutely needs a medium, something physical like air, water, or even a solid wall to travel through.
This is honestly the perfect way to picture it. Imagine a long line of people waiting for something. If the person at the back gives the next one a little push, that push is going to travel all the way down the line, like a domino effect. The push travels, but each person pretty much stays in their spot. That is exactly how sound energy moves through all the little particles in the air. And this, right here, reveals a huge difference between sound and, say, light. Sound is a mechanical wave. It needs those particles to pass the energy along. That makes it totally different from light, which is an electromagnetic wave. Light can just zoom right through the empty vacuum of space, no problem at all. Sound can't do that.
Okay, so we know the particles are getting pushed, but how exactly are they moving? Well, there's this fantastic little mnemonic that comes from classrooms in India that helps you remember the two main types of wave motion. PT Sir Nabola, sleep later.
And this phrase is just brilliant. The PT stands for perpendicular transverse. In a transverse wave, the particles move up and down, perpendicular to the direction the wave is actually traveling. A great example is when you shake a rope to make a wave. But the SL part? That stands for straight longitudinal, and that is our sound wave. The particles just push back and forth, straight along the very same direction the wave is moving. So, we know sound is a longitudinal wave, but why does a tiny whisper sound so different from a loud shout, or a deep drum from a high-pitched flute? Well, to understand that, we need a way to describe the wave itself. So let's look at its key characteristics. First up, we've got frequency. Just think of it as how fast the wave is vibrating. Basically, how many complete waves pass by a single point in just 1 second. We measure this in a unit called hertz, and our brain automatically translates frequency into a sound's pitch.
And yeah, the relationship is super direct. A higher frequency means a higher pitch. It's the difference between the low, deep boom of a bass drum, which has a really low frequency, and the sharp, high sound of a violin, which has a super high frequency. Simple as that.
Next, there's amplitude. The easiest way to think about this is as the wave's height. It really just represents how much energy the wave is carrying. Technically, it's the farthest distance a particle gets shoved from its comfy resting spot.
And just like with frequency and pitch, the connection here is really simple. A wave with a higher amplitude is packing more energy, and our ears hear that as a louder sound. A soft little whisper has a tiny amplitude, while a big, loud shout has a massive one.
Now, what's really cool is how all of these concepts are actually locked together with some pretty simple math. The time period it takes for one wave to pass is directly tied to the frequency, and the overall speed of the sound wave is just its wavelength. That's the distance from one peak to the next, multiplied by its frequency. This little formula is the key to everything from echoes to sonar.
Okay, so we know what a sound wave is and how to describe it, but, waves don't just travel in a straight line forever. They run into stuff. So let's explore what happens when sound hits a surface, what I like to call the bounce.
Oh, you've definitely experienced both of these. An echo is that single, clear, distinct repetition of a sound. Like when you shout across a canyon and hear, hello, 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 back. For your brain to hear it as a separate sound, the reflecting surface has to be over 17 meters away. Now, reverberation, or reverb, that's the messy jumble of tons of reflections all bouncing around in a smaller space, like an empty room. It's what makes the sound seem to linger and fill the entire area.
But, okay, this is where it gets really cool. The sounds that we can actually hear are just a tiny, tiny sliver of the full spectrum of sound that exists. Beyond what we can perceive, there's a hidden world of sound with some incredible superpowers.
I mean, look at this. The range of human hearing is surprisingly narrow, usually from just 20 Hz up to about 20,000 Hz. Any frequencies below that are called infrasound, and anything above it is the incredibly useful world of ultrasound.
And that high-frequency ultrasound is practically a superpower. We use it for all sorts of things, to gently clean delicate electronics, to find invisible cracks deep inside steel bridges, to see inside the human body, and even to shatter kidney stones without making a single cut. It's the exact same tool bats and dolphins use to navigate in complete darkness. How amazing is that?
And this brings us to one of the most brilliant applications of everything we've talked about so far. We're going to put all the pieces together. Let's dive into how sonar systems use sound to literally see where light can't go.
The technology is called sonar, which is an acronym for sound navigation and ranging. At its core, it's a technology that lets ships and submarines create a detailed map of their dark, watery surroundings using nothing but sound waves, echoes, and a little bit of math.
The process itself is beautifully simple. First, a transmitter on the ship sends out a quick pulse of ultrasound. That pulse travels out through the water, hits something, like the seafloor or another submarine, and bounces back as an echo. Then a detector on the ship listens for that returning echo. And here's the genius part. Because we know exactly how fast sound travels in water, the computer can calculate the object's precise distance just by timing how long that round trip took.
And that brings us all the way back to our riddle from the beginning. Can you make a sound that can't be heard? Yes, absolutely. We now know that sound is a mechanical wave. It needs a medium. So in a vacuum, like on the surface of the moon, there are no particles to carry the vibration. You could be ringing a massive bell, but without a medium, that energy has nowhere to go. No wave is ever created, and so no sound is heard. So let's end on this thought. If we can learn to harness a simple vibration to map the entire ocean floor and even see inside solid objects, what other invisible forces are all around us, just waiting for us to figure out how to use them? Thanks for watching.